you have to be able to try to meet a certain amount of criteria and show them what you plan to do, because you've got to show how you're going to meet the interest, convenience, and necessity of serving the public. Okay, this is the frequency allocation map, or it's the radio spectrum. Okay, so what they do is they allocate spectrum space, right? Say that Mrs. Peterson wants to, she applies and she's going to have a television station, and I've applied and I'm going to have one. Well, what channel are we going to be on? Can we be on the same one? Not in the same market, because then you're going to have all this problems, right? Radio stations. There are approximately 92 radio stations in the Dallas-Fort Worth metropolitan area. Did you have any idea there are that many of them? Because a lot of them are little kind of peanut whistle, ma and pa type radio stations out there. There's usually about the top 7 or 8, and they make most of the money, and they have the lion's share of the listeners, and then there's all the other also ran ones. But those fragment up the pie, right? They all take market share, and they take ears that people listen. And so when I would go into a market to fix a radio station and make it profitable and get audience, well, all those little ones count, because those are ears or people, you know, that's audience, or called cumulative audience, or cum, that you want to go and generate. Cum is the audience you have. Cumulative audience is short for cumulative, like X number of people. And then the other way that ratings are measured is not only cum, how big is your audience, but then how long does that audience listen? And that's called TSL, or time spent listening, in the radio world. They have the same thing, quasi same thing, for television viewing, only it's measured a little bit differently. They work on share of voice rather than cumulative audience, although they do. Now, let me give you some perspective, and I'm getting a little far afield, but I want you to understand why there's all these different designations here. And this is why I wanted a bigger screen. Look at that thing, that's a mess. I mean, that is really, really, really incredible when you look at it. You think, oh my goodness.
Market.
What's that?
This is per market.
No, this is the entire for the United States.
Okay.
These are the frequency allocations on the electromagnetic spectrum, which I'm going to show you in a minute. And I don't want to bog down and get too far in the weeds, but it's kind of important to understand what drives all this and why the FCC becomes very necessary. Each one of those little segments represents different frequencies on the electromagnetic spectrum. Who knows what the electromagnetic spectrum is? You ever heard of that? Yeah, go ahead.
Yes, you all have. I know you have.
You've heard of it, but you might not be exactly familiar with what it is. Essentially what it is it is a natural law of physics that things in the world, in creation, oscillate, right, or have a frequency to them. There's a frequency pattern to almost everything, from extremely low frequencies to extremely high. And those properties, just the variance in frequency, completely changes the way that wave works and what it does and how it affects us as human beings. And I'm going to show you that in just a moment. But this is just the radio spectrum, which is only a part of the electromagnetic spectrum. You with me? And so I'll show you that in just a moment. But you see all these little tiny, teeny designations here. Well, those are all really, really important, because maybe this is allocated to GPS, and so is that one there. And then, oh, you know, it's grandfather. You see that big blue block up there? That's AM radio. And then there's television in the big blue ones, and FM radio and so forth, and GPS. Who here ever uses wireless headphones? Anybody? Okay, what drives that and connects that to your smartphone? Bluetooth. Is that a frequency? Is that a wave? Absolutely, it's wireless. So it's going from your wireless headphones to your cell phone or iPad or whatever. You could be listening on a, you can hook up Wi-Fi to your desktop too if you want to. Or your television. I'm not blessed enough to have a brand new, really smart TV, right? And man, I'll tell you what, it's got all kinds of Wi-Fi stuff, and you can hook anything to it real easy, just natively. You don't need Apple TV to do it and stuff.
We don't use this, but our cameras do that too.
The cameras are Wi-Fi? Okay, now or Bluetooth. What's really cool about Bluetooth is extremely low power. Extremely low. Why is that a good thing?
The battery lasts longer. The battery lasts longer.
Well, that's true. The battery does last longer. It's a good point. But that's not the primary reason that it's extremely low power. Bluetooth is very, very low power so that it doesn't interfere with everybody else. Because it's a very personal connection typically. You notice if you get from one end of your house to the other, sometimes you'll lose your Bluetooth
Because you don't
connection.
have the-
That's why it's not very powerful at
it's-
all, on purpose, and they did that on purpose. Well, that's allocated in one of those little bands there. So, I mean, all this stuff is in this electromagnetic, or actually on the radio spectrum. Let me show you what it is. Did you see that one blue line? I don't know if you can read that, but that says, broadcast, that's the FM radio section right there. TV channels 5 and 6. Channels 2 and 4, or that other blue section right over there. So it went from this piece, and there it is, blown up, and that's from 88 to 108 megahertz. That's every FM radio station out there is in that little spectrum, that little slice of spectrum. So that's the entire radio spectrum, and it's just a little piece of it if you're listening to, or a tiny, tiny, tiny sliver of it if you've got your Wi-Fi going, even, which is on there. Your
When
GPS.
he says radio, and he's already said it, it is including television as well. You already said it, but you're saying these are the radio bands, but it also is including the television. That's
Yeah, TV, okay, so television, for example, this is TV, that one is, that one over there is, this one down here, there are a couple of them. Those blue ones are radio and television frequencies.
But that's not the same thing as Netflix.
It is not the same thing as Netflix. That one is a little harder to explain, but Netflix does show up here because of the fact that it is carried over the air at least part of the way, because what Netflix does is they generate content, right? And that content is aggregated to a transmitter that shoots it out into outer space to a satellite. That satellite then is bouncing that signal to a whole bunch of different receivers out there called cable operators and so forth. Then the cable operator takes that signal that they receive from Netflix and they put it out over their network, right? Wi-Fi, typically. And you've got a modem at your house, right? That signal is coming in.
But cable used to be different, which is why it was called cable. Because the sound was brought in through a cable.
Same principle though, but it's coax cable that is delivering a signal from that distributor to various outlets, to your home or business or whatever. And they would carry programming that typically was just the TV stations. Like who has AT&T, Uverse, or Spectrum, right? And you can tune in, the 500 channels or the ones that you picked and everything. Well, that's being distributed from a distribution point. Now let me show you something else here. I'm going to move on a little bit. But here's the electromagnetic spectrum I was talking about. All those little bitty pieces that I just showed you on the last slide all fit within the radio wave section of the electromagnetic spectrum. So if you look down here, this represents a meter in actual physical size. A meter is close to 3 feet, not quite. On the far left, see where it says 10 to the third power? So how many meters would that be? Who's a math person?
No, 10 to the third.
1,000, right? That would be 10 times 10 times 10, right? I'm not a math guy, but that was not too tough. So that's 1,000 meters. That means there are waves out there in the physical world that are 1,000 meters high. Typically sonar in the ocean, for example. As it moves and the frequencies tighten up, you'll see it gets to 1, that's in the radio wave spectrum. So the radio waves that are all around us that we can't see or feel, that are just passing through us and around us right now in the air, are probably about this big. Kind of weird to think about. Now, as you get higher, they turn into microwaves. They cook our food. So those are pretty useful, but it's all waves on the electromagnetic spectrum. They're related to radio waves, but they're different. They cook our food. You go a little higher, infrared. That's heat, right? A little higher than that, visible light. That's what we can see. Higher than that, ultraviolet. That gives you a sunburn. You get a little higher than that, you've got X-rays. That goes through and takes a picture of your bones because it passes through you. And get up to gamma rays, those will kill you. So they get really, really, really tight and really small. And they go from really big to really small. So that's the electromagnetic spectrum.
Here's a methodological question. What kind of waves would they use in a stun gun? Like in Star Trek?
I don't know.
But would they be more on the low side or the high side?
Shoot you with gamma rays?
They would probably, well, where would they probably be?
High,
wouldn't it?
I would think so.
So in Star Trek, they can set it to stun, or they can use it full out, what do they call it? They
Death?
Now again,
can- More like, it's not true, it's fiction. But
Right.
it would be more on the high range.